Look at a microcontroller like the ESP32S3. For $50, you get Wi-Fi, Bluetooth LE, LoRa mesh radio, and a dual-core 240 MHz processor. The embedded community treats devices like this with a rigid orthodoxy. Pick one function and write firmware to execute it. The workflow reflects this. You flash the chip, and it runs that loop until wiped for a new job. Pisces Moon OS pushed the hardware past these cultural assumptions. Instead of sequential operations, Pisces Moon OS splits the architecture. Core 0 locks into a persistent background process, while Core 1 simultaneously manages an independent array of active user applications. Architectural protocol, rather than silicon physics, defines the limits of this hardware. Reaching this level of concurrency required deconstructing 6 specific myths the industry believed about processing, memory, and hardware constraints. Accessing the full capacity of these chips requires moving past simple sequential loops and building strict OS-level resource arbitration. The first misconception is that a dual-core microcontroller is effectively bound to one primary operation at a time. Pisces Moon OS isolates those cores. It assigns Core 0 to a persistent background service called the Ghost Engine. The Ghost Engine runs continuously. It handles wardriving, scans for Bluetooth LE devices, and logs GPS coordinates, operating independently from the user's actions on Core 1. Pushing the processor this hard immediately hits a second constraint: the belief that the chip's 320 kilobytes of internal SRAM is enough for general-purpose computing. If you track over 100 Bluetooth devices while rendering a 60 frame per second interface, that memory rapidly fills up and crashes. Because the heap allocator fails based on whichever specific request pushes it over the limit, the crashes manifest as random, unrelated bugs across the GPS, the UI, or the radio. The hardware actually has 8 megabytes of external PRAM available. Redirecting the heaviest memory allocations to that external capacity requires only a single compiler flag. Raw hardware capability is only useful if the OS routes heavy loads to the correct physical locations. The third myth involves physical data pathways, specifically the unstated assumption that you cannot share the SPI bus under concurrent sustained load. On the hardware board, the microSD card and the LoRa radio module share a single SPI bus. When they attempt to transmit heavy data loads simultaneously, the physical packets collide. This causes a fatal hardware exception. The device crashes with a different memory address every time, making it nearly impossible to reproduce on a test bench. Previous developers avoided this because they used the microSD card and the radio sequentially. To run both simultaneously, the OS uses a traffic controller called the SPI Bus Treaty. It mandates strict behavioral rules. Components hit the bus and run, hold times are strictly capped, and metadata operations clear the path quickly. Controlling the bus leads to the fourth myth, the idea that synchronizing tasks across 2 processor cores is straightforward. Bench testing rarely exposes dual-core synchronization failures. They emerge in dense, real-world RF environments like downtown Los Angeles, detecting 80 access points at once. This network density forces the background Ghost Engine to write packet data to the SD card multiple times per second. If Core 1 attempts a standard user interface read at that exact fraction of a second, the dual access corrupts the SD card's internal linked list, throwing the system into an infinite loop. The solution is a free RTOS mutex semaphore, a strict lock and release mechanism that blocks one core from the SD card while the other finishes its transfer. Stable architecture requires this level of strict arbitration because chaotic field conditions expose concurrency bugs that sterile lab environments hide. The fifth myth centers on data protection, the assumption that you must use standard AES encryption to secure sensitive files on constrained hardware. AES encryption takes time. Wrapping data holds the SPI bus open so long that it violates the SPI Bus Treaty, jamming the queue and crashing the OS. The objective is keeping data inaccessible to an adversary. Encryption achieves this, but so does severing the access path. Pisces Moon OS maintains index files acting as maps to internal data structures. Deleting the index orphans the data, making it unreachable. Deleting metadata takes milliseconds. It secures the device from software forensics while adhering to the tight time limits of the SPI Bus Treaty. The final myth is the most mundane, assuming hardware from the same manufacturer is identical across production runs. The LilyGo TDEC Plus shipped in 2 undocumented production batches. The boards look identical, but contain different GPS modules running at entirely different baud rates. When the OS tries to initialize the wrong module, the failure is silent. The hardware simply refuses to work. Code cannot assume consistency. It requires an auto-detection script that verifies a valid data structure before latching to a configuration. Over-relying on standard practices, whether forcing AES encryption on an overloaded bus or trusting a manufacturer's spec sheet, creates artificial constraints on the hardware. For years, the industry limited powerful microcontrollers by relying on simplistic software habits. By combining independent core loops, PS RAM management, and bus arbitration gates, the hardware handles immense concurrent load without collision. These layers interact to provide a functional foundation for complex software on a $50 chip. These formal resource management protocols provide the architectural standard for concurrent multi-subsystem software on the ESP32S3 hardware class. Breaking points only surface when you push the hardware out of the lab and into sustained field conditions. The limitations of embedded systems are rarely etched into the silicon. They exist in the assumptions of the architect. Mastering hardware requires moving past efficient code and formalizing the behavioral rules that govern physical physics.